Okay, so we've talked about the differences between reduction and oxidation. Um, let's focus in now on one of the differences between them, which is in terms of their oxidation numbers. So we said oxidation is an increase in oxidation number. Reduction is just a decrease in the oxidation number. What is oxidation number in the first place? Okay, so we're going to take a look at that, define what that is, and then we will look at the differences and how we assign oxidation numbers, etc. So when we look at oxidation numbers, oxidation number is also referred to, is also called oxidation number, ON, or sometimes it's called oxidation state, or OS. You'll see any of these four things being used to refer to the same concept, which is the charge an atom would have if all of the electrons were transferred completely to it. Okay. And there's some rules for identifying oxidation numbers or oxidation states for elements in a particular compound. And there are essentially two big things to keep in mind. Okay. When we assign the oxidation numbers, the first thing to keep in mind is that the oxidation number for an element in its elemental form is 0. So for instance, if I have zinc metal, the oxidation number here is 0. If I have hydrogen gas, which exists as H2 or diatomic, oxidation number there is 0. If I have fluorine gas, oxidation number there is 0 as well. If I have something like magnesium metal, the solid oxidation number there is 0. The second thing to keep in mind is that when you add together the oxidation numbers in any molecule, compound, or ion, etc., when you add them together, it must equal the overall charge on the species. So if you have any molecule, you add your oxidation numbers together, it must add up to 0. If you have a polyatomic ion, you add together all the oxidation numbers, it should add up to the charge on that polyatomic ion. The other thing, part of what goes along with the second point here is that if you have a monoatomic ion, the oxidation number is simply the charge on that ion. So for example, for the Na, well, let's look at the one up here. So if I have Mg with a 2 plus charge, oxidation number there is +2. If I have Mg, just a solid, oxidation number there is 0, right, as we saw above. So for the ion, monoatomic ion, oxidation number is simply whatever the charge is. Just as a quick aside, oxidation numbers usually have the sign first, plus or negative first, and then the number after. Whereas your charges, you've probably seen this already, the charges usually have the number first, followed by the plus or minus after, right? So for instance, we have Mg with a charge of 2 plus, but the oxidation number for Mg is actually +2. They're the same, it's just flipping the charges. It's not a huge deal, but some places, Alex, for instance, would be a little picky about that, so just be careful with that. All right, so when we assign oxidation numbers, in addition to what we just talked about here in the first two rules, there are some general things that we want to keep in mind when it comes to assigning these. And some elements are almost always going to have the same oxidation numbers wherever you find them. Fluorine, for example, if it's in an element, if it's in a compound, it's always going to be -1. Okay, so in the case of HF, for example, F here is going to be -1, and if this is an overall neutral thing, well, then we know the H has to be +1 to cancel out to give you 0. Okay, for the group 1A or group 2A metals, when you find them in a compound or a polyatomic ion, the group 1A are going to be +1s, the group 2A are going to be +2s, because those are the charges, these are the charges on their ions. For hydrogen, it's normally going to be +1, except when it's combined with a group 1A or group 2A metal. In that case, it's going to be a -1 in those compounds. Okay, so for instance, if you have HF like we saw here, it was +1, but if we have something like NaH, sodium hydride, well, based on the second rule, Na is going to be +1, which means the hydrogen has to be -1. Okay, oxygen is always going to be +2, except when it is combined with something higher on the list that causes it to have a different oxidation number, right? So if we take a look here at K, so H2O2, like H2O2. We know the H here is going to be +1, right? And we have two of them. So 2 times +1 would be +2. So that means that 2 of the oxygens here should equal -2, which means that 1O should be -1, right? But generally O is -2, except in these special circumstances. Your group 7A, the halogens, and again, other than fluorine, because the direct fluorine is always -1. These are always going to be -1, except if they're combining with anything higher up on the list that we just went through, where it would necessitate an oxidation number that would be different. Okay, let's take a look at an example. I have to actually go back to the example we looked at up here. Okay, so in the case of this reaction, so we have hydrogen and fluorine forming HF. So H elemental form 0, fluorine elemental form 0, and the total charge to the contribution to the overall charge, that's the number in the square, and you'll see this in your textbook as well. This is the notation that your textbook uses. In the case of HF, we just said H is always going to be, well, we know F is always -1, which means that H has to be +1. Okay, so if I look now, what's happening to the hydrogen? Hydrogen goes from 0 to +1, so H then is undergoing oxidation. F goes from 0 to -1. Its oxidation number is decreasing, so F undergoes reduction. So we can then say H is the reducing agent. And we can then say F is the oxidizing agent. Then we can summarize this in any general sense. We can say the reducing agent is oxidized. And then the opposite would be true, the oxidizing agent is reduced. Okay, when you encounter these terms initially, yes, it can be a little confusing. You have to slow down, start from first principles, and look at each individual thing, assign, is this undergoing oxidation? Is the oxidation number going up? Yes. Well, then it is the reducing agent. If this thing is undergoing reduction, is the oxidation number decreasing? Well, then it is acting as an oxidizing agent. Okay, if we look here at the second example, right, so we have nitrogen elemental form 0, hydrogen elemental form 0, hydrogen in a compound, when it's not combined with a metal, it's going to be +1. We have 3 of them, so the total contribution here would be the +1 times 3, give you +3. If the H is +1, we have 3 of them, then the nitrogen has to be -3 to cancel that out. Okay, and we have 1 N in the formula. A little contribution there of -3. So if I look at the nitrogen, it goes from 0 to -3, so it's undergoing reduction. Okay, the H goes from 0 to +3, the H undergoes oxidation. So the H there again is acting as the reducing agent. The nitrogen, which is undergoing reduction, is acting as the oxidizing agent. All right, let's take a look at identifying the oxidation numbers in KMNO4, and we'll use some of the rules we talked about before. All right, so we know that in KMNO4, which is potassium permanganate, potassium here has a charge of +1, I'm sorry, or 1+. Okay, so the oxidation number there is going to be +1. We know that the oxygens are always going to be -2, except with the exceptions we mentioned above, and these are none of the exceptions. So each oxygen is going to be -2, and we have 4 of them. So it gives a total contribution of -8. So I know what the oxygen, all of these here give me -8. The potassium gives me +1. So when I add all of these together, including what the manganese is, I should add up to 0. All right. So what I can do is I can make a little math equation. I can say +1 plus whatever the Mn is plus the -8 from the oxygen should give me 0, because in KMnO4, right, this thing doesn't have a charge, so the overall charge is 0. So my Mn then would be, I move everything else over to the other side. So +1 minus 8, this would be -7, plus Mn gives me 0. So the Mn would be 0 plus 7, would be, whoops, which would be +7. Okay, so we can calculate the oxidation numbers just by following those rules when we determine this. Okay, let's take a look at a one with a charge. So this is the chlorate ion, Cl3 minus. Okay, we know that the oxygen, each oxygen is going to be -2. We have 3 of them. That gives -6. Okay, for all of the those. So when I add together the -6 plus whatever the Cl is, I should get -1, okay, because that's the charge. That's the overall charge. So the chlorine there would be -1 plus 6. That would be what? Plus 5 for the charge, the oxidation number on the Cl. Okay, yes, there's a little bit of math involved, a little bit of science that we need to consider, but it's really not that complicated if you follow the rules, okay, and you slow down. It's very tempting to rush through this, and I guarantee you, if you do it, okay, you're going to run into some issues. So slow down and take your time, and pay attention to the signs and the numbers of each of the subscripts here for each of the elements that we have.